this particular matrix relationship, right, if you were to expand all these things out, right, isn't it going to be the same as the three equations on the screen on the right? Right? So for that case, if you don't want to use Gauss elimination, you can form three equations, three unknown, three equations, of course you can actually solve it. Right? But the thing is that, as I said, if your entire expression is a 4x4 matrix, then you have to form four equations and then four unknowns. It will be much more difficult to work it out. Right? So for that case, you might want to actually use the Gauss elimination method for you to actually determine the solution. Right, so either, if you are familiar with the Gauss elimination, you can actually use the Gauss elimination method. Eventually, you will be able to determine this. Right? Let me see. Yeah, correct. Right? So what you did was, from Gauss elimination, right, you will be able to derive it into this particular form. Right? So if you are able to reduce the matrix into the final form, in this case, you know that you always go with the last row first, right? So what does the last row say? The last row says is that, of course, because this is 0 multiplied by theta b, 0 multiplied by theta c, and it's actually 1368 multiplied by delta equals to minus 780. Right, so with that, that's where is your first expression over here, right? So from that, yeah, correct. So if this is the one, you can get that delta is equals to 2.12 divided by EA, right? And after that, once you've gotten your delta already, you can go back to your this particular matrix again, and you know that 0 multiplied by theta b is 0, so you have minus 184 multiplied by theta c plus 12 multiplied by delta is equals to 140. Right, from there, you work out the second equation, right? But the thing is that you already know what is delta already. You can put it to the second equation, and you will be able to solve what is theta c. Right, this is exactly what this particular second row is about. Right, so theta c, what you have done is that you will be able to calculate what is theta c. Theta c is actually minus 11.57 over EI. Right? So after that, you can then again move back to work on the first row. The first row is 48 multiplied by theta b plus 8 multiplied by theta c minus 24 multiplied by delta is equals to 20. So work it out, you already obtain the first two numbers already, and work it out through, you will get your theta b is equals to 13.16 divided by EA. So with that, you are basically able to prove that these three, what is the delta? What's the d, right? What's the d values? Where it is given in your question, you need to prove it. Right, so from there you get your theta b is actually 13.6, and your theta c is minus 11.57, and your delta is actually 2.12. Right, so that corresponds to the, okay, sorry, it's not 2, it's actually 9.12, sorry, because of the writing, so it's 9.12. So you can see that it actually matches well with what is actually given in the tutorial question. Right? Okay, so with that, right, that's not all, right? So the question states that, hey, then now you have to actually determine what is the bending moment at ends B and C of the member BC, right? So now you have actually calculated all the values, right? You have calculated all the values for delta, theta C, and theta B, right? So from there, you will know that what is the bending moment in BC, right? Remember, you have actually done at the beginning, right? You have actually draw this diagram, right? Correct? And you have determined these moments M1 and M2 using the slope deflection method. And over here, you know that moment at B in member BC is actually EI theta B plus EI theta C divided by 2. And you have already determined what's the value for theta B and theta C, right? So over here, this is also theta B and theta C. You can plug it back in, and you can calculate what is the moment at actually B and C for member BC, right? So from there, you can actually do that. But remember, for this case, right, is it just that straightforward that you actually, so for member B, Is it just straightforward EA theta B plus EA theta C divided by 2? No, right? You still have to actually add the fixed end moment induced in member BC. Remember in our example, page 8, right? So we actually gone through that already. If you want to calculate the moment, if let's say there's a fixed end moment induced in that member, you have to actually add on to whatever fixed end moment over here. And for this case, why is it minus 20? Why is it minus 20? Because you look at here, right? If you move up here, this is what you actually calculated, right? So because at node B, for member BC, this you have calculated that the FEM is minus 20. That's why it's 20 in the counterclockwise direction. So that's why it is actually a negative value, right? And the one in node C, it is actually 20 in the clockwise direction. So it's plus 20. So this is minus 20. So for B is minus 20 and C is 20, right? So we're moving that down. You would see that at node B, it has to be this expression plus, so it's my minus 20. It gives you minus 12.65 kilonewton meter, right? And how about the moment at C? So moment at C again is this expression, and now you have to add on to the FEM that is actually being induced, and for this case it's actually plus 20. So with that, you work it out to be actually 15.0 kilonewton meter. Right, so for that, it actually matches well with what the question is asking, to show that whether the moment at B and C are minus 12.6 kilonewton meter and positive 15.0 kilonewton meter respectively. Alright? Okay, so you can see for this case, for example 2, right, it is really a more intensive question. First thing is that it gives you the structure, right, and it then actually have a uniformly distributed load. And it's telling you that because of this loading condition, it induces there's a theta, okay, deflection at node B and the deflection at node C. And also there's a horizontal deflection movement, okay, delta, value of delta. So after that, you have to actually break it down, find the individual member equation, right? Then from there, you have to actually form what is the stiffness metric. And from the stiffness metric, you then have to calculate what's the P. And P has to be equal to PA minus PF. And after that, once you have that, you will be able to solve the equation to find out what is all the various displacement of theta B, theta C, and delta. Then you can actually find the moments at B and C, respectively. Alright, so this is actually based on the slope deflection method for question 1 and 2. Alright? Any questions on slope deflection method? Okay, so if not, what we can do is that we can take probably a 10 minutes break, then we can come back to go into question 3. Right? That's where you apply your moment distribution method. Alright?